Hello everyone. So in this video I'm going to talk about properties of binary trees. We are going to actually see a couple of definitions, some theorems. All of these are going to help us to understand, to analyze the time complexity of different methods related to binary trees that we will see in the upcoming weeks. So I'm going to first define a specific form of binary tree which is called perfect binary tree. So we will say a perfect binary tree of height h is a binary tree where all the leaf nodes have the same depth h and all other nodes are full. Okay, so this is going to actually look like something like this example that you can see. As you can see, all of the leaf nodes are at the same level, all of the leaf nodes are at the same depth, the height of all of them, the depth of all of them is h, and all other nodes that we have are going to be full. So this is just like you grow a binary tree. Let me actually just give you some other example of a perfect binary tree. If you just have one node, okay, the perfect binary tree that you have is going to be just one node, which is going to be the root and a leaf node. As you can see, this is following exactly the same, all of those definition in a perfect binary tree. If you wanted to actually create a binary tree of height 1, it is going to actually look like this. So you need the 3 nodes if you want to create a perfect binary tree of height 1. A tree like this one is not going to be perfect, right? Because it's correct that all the leaf nodes are at height 1, depth 1, but this node is not full, right? So it's just like you are missing a node here. If I'm going to create a perfect binary tree of height 2, it will be of height 2, it will look like this, that you are going to have actually 3 levels and all the nodes are complete, all of them are full. If you are going to create a binary tree of a perfect binary tree of height 3, it will look like this. And this is actually an example of a perfect binary tree of height 4, right? This one. So you can see that it is, in fact, following a specific pattern, and it forces you to have a very specific number of nodes. If I have a perfect binary tree of height 0, it's going to be just one node. If I have a perfect binary tree of height 1, it is going to need 3 nodes, right? If I have a perfect binary tree of height 2, it's just like you can actually find some formula for this. This is going to actually give me some pattern for the number of nodes. This is full here, just one node at this level. Then I need 2 nodes. Then I need 4 nodes. How many nodes in total? The total number of nodes here is going to be 7. I can actually just follow the same rule. One node for the root, then 2 nodes for the next level, 3 nodes, and 4 nodes at this level, right? And 8 nodes at this level. How many nodes in total? It is going to be 15. And now you can actually see that there is going to be a pattern for the number of nodes in a perfect binary tree of height h. These formulas are going to be important for me. I'm going to exactly work on this kind of theorem here. So let's just discuss that if I have a perfect binary tree of height h, how many nodes I would have. Instead of actually count them, I can try to find a formula for that. I need one node at height 0, then I would have how many nodes at height 1, how many nodes at height 2. It's actually, you can see that this is going to be all the powers of 2 from 0 to the last level, which is going to be at height h. So I need to actually get the summation of all these nodes. And we know what is going to be this summation. Remember, this summation of I equal to 0 to h, 2 power I, it will be equal to 2 power h plus 1 minus 1. This is exactly the first theorem that I'm going to prove about perfect binary trees. And actually, I just discussed it here, but I'm going to prove it, mathematically, more formal proof. So to be able to prove not only that theorem, I'm going to actually show you 3 other theorems that if I have a perfect binary tree with n nodes, I know that the height is going to be in theta of log of n. And if I wanted to actually to be more precise from this formula, if I can prove this formula, I can basically find a complete formula for the height of a tree with a perfect binary tree with n nodes, which is going to be log of n plus 1 minus 1. Or for example, the number of leaf nodes in a perfect binary tree of height h is going to be 2 power h. And the last theorem is the average depth of a node in a perfect binary tree is going to be log of theta of log of n. Okay, I'm going to prove all these 4 theorems, but to be able to do that, I need a more formal definitions for the perfect binary tree. This is the standard definition of perfect binary tree, but I wanted to rewrite this definition in a recursive form. Then using that recursive form, I can do the proofs much easier. So I can write a recursive definition for a perfect binary tree as follows. You can see that this recursive definition is very similar to what we have discussed for a binary tree. We are going to have a base and we are going to have a recursive relation part. What the base is telling me, the base tells me that what is the smallest perfect binary tree. We would say that a binary tree of height h equal to 0 is going to be a perfect binary tree because you are going to have just one node, right? And when you have one node, this is going to be your root node, and it is a perfect binary tree. This is the smallest perfect binary tree that you can have. Then the recursive part is telling me that a binary tree of height h greater than 0 is going to be a perfect binary tree if it has exactly 2 subtrees and both subtrees are perfect binary trees, and not only that, the height of both of them should be h minus 1. So if you have a perfect binary tree of height h, it needs to have 2 subtrees, both of them should be perfect, and the height of both of them should be h minus 1. Okay, so you have a perfect binary tree of height 0, it is going to be another perfect binary tree of height 0. Then you can create a larger perfect binary tree of height 1 by just adding these two to add one more node as the root and combining these two. right? You have, this is a perfect binary tree of height h equal to 1. If I have another perfect binary tree of height h equal to 1, so this is 1, and this is another one, I can create a larger perfect binary tree by just combining these two, right? So you can see that both of the subtrees should be perfect, and both of them should have height h equal, height h minus 1. So this is going to be a perfect binary tree of height h equal to 2. So this recursive definition simply is going to help me to prove this theorem, that in a perfect binary tree of height h, the number of nodes is going to be 2 power h plus 1 minus 1. How I'm going to prove this? I'm going to exactly use that recursive definition. I'm going to, when you have a recursive definition, you can do your proof using induction. So I need a base case. So the base case is that when h is equal to 0, I should prove that this theorem gives me the correct number of nodes. If h is equal to 0, so it means that I am going to have a tree with just one node, right? Now let's look at the that formula in the theorem. The formula in theorem is going to tell me that the number of nodes is going to be 2 power h plus 1 minus 1. What is h? H is equal to 0. This is going to be 2 power 0 plus 1 minus 1. This is going to be 2 power 1 minus 1. This is going to be 2 minus 1. This is going to be 1. Right? The formula exactly give me the correct number of node. So now I am going to prove the inductive step for the induction. The inductive step has one assumption that tells me that assume the theorem is correct for all trees of height less than h. Equal to h. Okay, you can actually just assume it. This is correct. The theorem is correct for all the trees of height less than h or less than or equal to h, and then prove that the theorem works for h plus 1, the height of h plus 1. Okay, so if we know the theorem is correct, this is a part of our assumption. We know that the theorem is correct for all the trees of height h and less than h. When I am going to create a tree of height h plus 1, which is a perfect binary tree, the recursive definition tells me that I need to have a root node, and the root node needs to have exactly 2 subtrees. Each of them should be a perfect binary tree. This is a perfect binary tree, this is a perfect binary tree, and the height of each one should be h. Okay, a perfect binary tree of height h. So this is a perfect binary tree of height h. What I know about this is that the number of nodes should follow that formula. So the number of nodes in this subtree is going to be 2 power h plus 1 minus 1. And the number of nodes in this subtree also is going to be, I'm going to call it n prime. This is going to be again 2 power h plus 1 minus 1, because this is again a perfect binary tree of height h, right? So the number of nodes in this larger perfect binary tree, what is the number of nodes? This is going to be whatever I have here plus whatever I have here plus 1 because of this root node, right? So it's going to be n plus n prime plus 1. I'm going to exactly just follow the formula, add these two together, plus 1. This is going to be this formula. The number of nodes in the left subtree, the number of nodes in the right subtree, this is that n prime, and plus 1 for the root. If you add these numbers, you can exactly see that the result is going to be 2 power h plus 2 minus 1. So if I'm going to just write down here, if you expand this parentheses, this is going to be 2 power h plus 1 plus another 2 power h plus 1, right? These two terms are equal. So minus 1 plus 1 minus 1. You can see that this result, I can write it as minus 1, right? And these two terms are the same. So it is just like you have 2 multiplied by 2 power h plus 1 minus 1. So I can rewrite this as, just put this 2 in the power. So this is going to be 2 power h plus 2 minus 1. This is exactly the formula that we had. This is telling me that for a tree of height h plus 1, what is the number of nodes? The formula was 2 power the height plus 1 minus 1. This is exactly this formula. So we proved that the number of nodes in a perfect binary tree of height h is going to be 2 power h plus 1 minus 1. So from this, I can use this theorem to prove the next theorem. The next theorem is actually telling me that the height of a perfect binary tree, if I know the number of nodes in a perfect binary tree, I can calculate the height. It is just the reverse of the previous formula. I know that in a perfect binary tree of height h, the number of nodes is going to be 2 power h plus 1 minus 1, right? So now I can just try to find h based on n. So I'm moving 1 from this side of equation to the other side. Then because I wanted to actually find h, I will take the log from both sides. Log of n plus 1 is going to be h equal to h plus 1, and put the 1 to the other side of equation. So this is going to be the formula. The height of a perfect binary tree with n node. So if I know that the perfect binary tree has, for example, 15 nodes, I can calculate the height for that. For example, in a perfect binary tree with 15 nodes, what is the height? The height is going to be log of 15 plus 1 minus 1. This is going to be log of 16 minus 1. This is going to be 4, right? Minus 1, this is going to be 3. The height is going to be 3. And if you actually going to draw it, this is going to look like this. Right, you have 15 nodes, and the height of the tree is 3. So we usually, instead of just going with this formula, this is something that you don't really need to memorize this if you just know that the other formula that was n equal to 2 power h plus 1 minus 1, you can always just get that formula from this one. So you just need to memorize this, which is not really hard to memorize. Even if you actually forget about that, try to draw a couple of perfect binary trees and you can simply just find the formula. The thing is, we usually write down this theorem instead of exact formula. The thing that we care about is that this log of n plus 1 minus 1 is actually in theta of log of n. And this is something important for me. It's actually telling me that if I have a binary tree which is a perfect binary tree, the height based on the number of nodes is going to be log of n. It's telling me that the tree is actually short, right? Remember we discussed about the worst case and the best case of the height based on the number of nodes. That if your tree just grow one way, this is bad, right? So it's just like you have n node, instead of creating it as a linked list, you are creating it as a tree, but still this is a linked list because it is just growing one way. So instead of this, you could create a tree which is much shorter, right? And when it is shorter, it's going to affect how much actually work that you need to do. For example, it started from here, you're searching for an item. From here, you go here, and then from here, you go here, and you finish. So the time complexity for us in a perfect binary tree is going to be way less than the time complexity in a tree which just grows one way. So let's go back to the next theorem. The next theorem is talking about the number of leaf nodes in a perfect binary tree of height h. This theorem is telling me that the number of leaf nodes is going to be 2 power h if the height is h. Again, I can prove this using induction. I have a base case that's telling me that show that if h is equal to 0, the formula is correct. When h is equal to 0, it means that you have only one node, right? And that node is going to be a root node. And it is a leaf node as well. So how many leaf nodes you have in a tree that only have one node? The number of leaf nodes is going to be 1. What the formula tells me? The formula tells me that the number of leaf nodes is going to be 2 power h. 2 power 0, it is going to be 1. So the formula is correct for the base case. And now I'm going to prove it for the inductive step. The inductive step is that I am assuming that the formula is correct for all trees of height h. I'm going to prove that the formula is also correct for perfect binary trees of height h plus 1. So this is a part of our assumption. We assume a perfect binary tree of height h is going to have 2 power h leaf node. I am going to prove that a perfect binary tree of height h plus 1 is going to have 2 power h plus 1 leaf node. So, the proof here is actually very easy. And the reason is that in a perfect binary tree of height h plus 1, you are going to have 2 subtrees. Both of those 2 subtrees are going to be, so what is the height here? The height here is supposed to be h plus 1, right? And in a perfect binary tree of height h plus 1, you should have exactly 2 subtrees, right? And which each one is going to be a perfect binary tree of height h. How many leaf nodes I would have here? The formula, this assumption is telling me that I would have 2 power h leaf node, and I would have 2 power h leaf node here. So how many leaf nodes in total I would have in this bigger perfect binary tree? Whatever is the number of leaf node here plus the number of leaf node here. So this is going to be 2 power h plus 2 power h. 2 multiplied by 2 power h. This is going to be 2 power h plus 1. So we are done. We proved that in a perfect binary tree of height h, the number of leaf nodes is going to be 2 power h. Something interesting about this is not really it. We have already actually proved the previous two theorem. It is just a conclusion from the other two. But there is something interesting here, that I know that in a perfect binary tree of height h plus 1, the total number of nodes is going to be 2 power h plus 1 minus 1, right? And the number of leaf node is going to be 2 power h. So basically it's telling me that half of the nodes, whatever you have, more than half of it is actually are going to be leaf node. If you think about it, this is something interesting. For example, if I have 7 nodes in my perfect binary tree, 4 of them are going to be leaf node, right? If I have, this is more than half of it, but it's exactly half of it plus 1. I mean, if you add 1 to that and then divide it by 2, this is going to be the number of leaf node. Or for example, if you have 15 node in your perfect binary tree, 8 of them are going to be leaf node. Right? 8 of them are here. All the other nodes are going to be just 7, and then 8 of them are going to be leaf node. This is interesting because this is going to actually lead us to the next theorem. The next theorem is about the average depth of a node in a binary tree, in a perfect binary tree. This theorem tells me that the average depth of a node in a perfect binary tree is going to be log of n. Why this theorem is important? Because it's telling me that if you are doing some specific computation over all of the nodes in your perfect binary tree, or just randomly choose one node from your perfect binary tree and do some computation that depends on the depth of that node, the time complexity is going to be log of n. This is something very interesting, and when we talked about the heap, you will see that it helps us to prove the time complexity for the heap, that many actions are going to be log of n, and it helps us in that discussion. So now let's actually see that how we can prove this this theorem. Remember what was the depth for each node? The depth for each node is the distance from the root node. So the distance of the root node to itself is going to be 0. So the depth of root is going to be 0. The depth of all the nodes at the next level are going to be 1, right? Because the distance is going to be 1. So the depth of the children of root is going to be 1. The depth of all the nodes at this level is going to be 2. It's just like whatever is the depth of the parent, the depth of all the children is going to be the depth of the parent plus 1. So this is going to be 2, 2, 2, 2. The depth of the nodes in this level are going to be whatever is the depth of the parent plus 1. 3, 3, 3, 3, 3, 3, 3, 3. And so on, right? The depth of all the nodes at this level are going to be 4, and the depth of all the nodes at this level are going to be 5. Give me a pattern to calculate the average depth of all of the nodes. So if I'm going to calculate the average depth, I need to get the summation of depth of all the nodes, then divide it by the number of nodes that I have. Okay, so what is that pattern that I can actually follow? The number of nodes at depth 0 is going to be 1, right? This is going to be depth 0. just the root node is at depth 0. So how many nodes I have at depth 0? 1. How many nodes I have at depth 1? 2 nodes, right? All the children of the root. So 2 nodes which are at the depth 1. How many nodes at depth 2? All the children of these 2 nodes. So it's going to be exactly, you multiply it by 2. I am going to have 4 nodes at depth 2. I'm going to have 8 nodes at depth 3. I'm going to have 16 nodes at depth 4 and 32 nodes at depth 5. Right? So there is going to be exactly a pattern here. What I need to do is just get the summation over all of this. And because I don't know what is the depth, I'm going to actually talk about a perfect binary tree of height, for example, h. Okay? So let's actually write down a formula for this one. If I'm going to get the summation of the depth of all of the nodes, I need to multiply the number of nodes. So for example, I have one node at depth 0. So the depth of the first node, the root node, is 0. Then I have 2 nodes at depth 1, right? Then I have 4 nodes at depth 2. Then I have 8 nodes at depth 3. I need to get the summation of all of this, right? So I can find a formula for this. I can just multiply the count to the depth. It is going to give me this formula. I to 2 power I. And how many level I need to actually change? This is going to be started from I equal to 0 to h. So this is going to be the total summation of the depth of all the nodes. I wrote it here with the index k instead of I. So this is the summation of depth of all the nodes. And then I need to divide it by the number of nodes so that it gives me the average depth. If I randomly pick a node from the perfect binary tree, what is to be the average depth of that? So I need to divide that summation to the number of nodes. How many nodes I have in a perfect binary tree of height h? I know the formula from the previous theorem. This is going to be 2 power h plus 1 minus 1. So I know that this summation looks very actually complicated, but there is a nice formula for this summation. I don't want you to memorize this, but I thought that it's good to just write it down. It is going to be more clear that what would happen here instead of just giving you the formula. So this summation is going to be, this is the formula for that summation. Okay, I can factor out this 2 power h plus 1, right? And write it down as 2 terms of, you can see that I have this plus 2, so I have rewrite it in this form. So that I would have actually 2 terms in this form. It's just trying to simplify the formula. We can this is just math, just working on the formula, and at the end what I'm getting is that you can see that by just factoring out these 2 terms, I'm trying to actually find something similar to the denominator. So this is going to be h minus 1 multiplied by 2 power h plus 1 minus 1. This is exactly the denominator, so I can take this h minus 1 out. So I have h minus 1 plus this actually term. One thing that I know about this formula is that I don't want you to memorize this exact formula. The thing that we care about is we can write this formula in terms of the lambda notation, so it is clear that this is going to be theta of log of n, right? Because we already know that this is going to be, this term is going to approach to 0, right? Because the denominator is way bigger than numerator. If h is going to approach to infinity, if the number of nodes is approaching to infinity, so this term will disappear. You will actually just end up with this term, and we already know that h is going to be in theta of log of n, right? So in total, I can say that the average depth of a node in a perfect binary tree is going to be theta of log of n. So all of these theorems, I have discussed them here because we want to use them when we discussed about the binary search trees, when we discussed about AVL trees, when we discussed about heap. So these are the theorems that I'm going to actually refer to them later. A nice thing about all of these theorems that we proved is that if I can create my tree to look like a perfect binary tree, I can prove that all the operations that you can do, which depends on the height of the tree, all of those operations will be in theta of log of n, because I know that the height of the tree is going to be in theta of log of n in perfect binary tree. So if I can create my binary tree to be like a perfect binary tree, I am going to avoid that worst case of theta of n. Remember that we discussed the height of the tree in the worst case. If you don't put any restriction in over the structure, over the form of a tree, it can be theta of n. It can be linear. Then the height of the tree can be linear. So we are going to try to create trees that looks like a perfect binary tree. But you have already actually seen that there is an issue with a perfect binary tree. So, for example, if I have only 2 nodes, can I create a perfect binary tree? No. If I have 2 nodes, either the tree will look like this one or this one. This is not going to be a perfect binary tree. If I have 4 nodes, can I create a perfect binary tree? No. The tree would look like, in the best case, the tree is going to, it's just like I'm trying to fill all the levels, right? But the tree is going to look like this. You can see that something is missing in the last level. So perfect binary tree is very restricted form of a tree. It forces you to have your number of nodes to follow this formula, right? So that 2 power h plus 1 minus 1. So you should have 1 node or 3 node or 7 node or 15 node, any number except this sequence that we can see here cannot create a perfect binary tree. So perfect binary tree is very restricted. If I have 3 nodes, if I have 4 nodes, if I have 5 nodes, if I have 6 nodes, I should be able to create a good tree that the height of it is going to be log of, and I wanted to be able to create such a tree. That's why I'm going to explain, I'm going to give you a definition of the next a specific form of a binary tree, which is called complete binary tree. We would say that a complete binary tree is going to create the tree by filling all the levels from top to bottom and from left to right. So for example, if you have only 2 nodes, put 1 as the root and then try to actually fill all the nodes in the next level. So this is going to be a complete binary tree, right? And then if you have 3 nodes, how you are going to actually just increase it, you are going to add another node here. Then if you have 4 nodes, this is going to be a complete binary tree. If you have 5 nodes, you add one more node in the last level from left to right. If you have 6 nodes, if you have 7 nodes, if you have 8 nodes, you can see that this is full, this is full, this is full. If I have 8 nodes, the complete binary tree is going to look like this. If I have 9 nodes, it will look like this. If I have 10 nodes, it will look like this. So in fact, in a complete binary tree, it's just like you are trying to follow the shape of a perfect binary tree, but you don't have enough nodes, right? So feel all the levels from the top, from top to bottom, and from left to right. This is exactly following actually the way that you look at the nodes in a birth first order. Okay, this node, then you are full, you have actually filled that level, then you fill this one, then you add one more node, then you have, if you have another node, you actually put it in the next level. If you have another node, you put it here, right? If you have another node, you put it here. If you have another node, you put it here, and so on. This is going to give me a complete binary tree. Something nice about complete binary tree is that if you have any number of nodes, you can create a complete binary tree. In a perfect binary tree, if you wanted to actually create a perfect binary tree, the number of nodes that are valid is going to be 1, 3, 7, 15, 31, and so on. So many numbers are not covered. But if you have any number of nodes, you can create a complete binary tree. Okay, so it is very less restrictive in the form of a tree. But the nice thing about complete binary tree is that although this is not perfect, but still I can prove that the height of a complete binary tree, with a node is going to be the floor of log of n. So at the end, I can actually write a height of a complete binary tree in the form of theta of log of n. And this is something that we care about. Okay, this formula, try to actually just work with that. For example, try to create a complete binary tree of height 9 and see that what the formula tells you about the height of the height. A complete binary tree with 9 nodes, with 10 nodes, with 30 nodes. Let's actually see that what the formula is actually telling you. I don't want to prove this theorem because this is going to be actually very complicated, but all those theorems that we discussed about perfect binary tree, we can prove them, not the exact formulas, but we can prove that the height of a perfect binary tree is going to be a height of a complete binary tree with n node is going to be log of n, theta of log of n. And not only that, the average depth in a complete binary tree again is going to be theta of log of n, the average depth. I have some extra slide that exactly prove this, all of it, these two main theorems about the height and about the average depth. But I just put them here for your, if you are actually interested, you can go through these theorems, but I'm going to skip them from the class. These details are just, the math is beyond the scope of this course, so I'm going to skip them. So this is the end of this video. Please listen to this one, and if you had any question, we can discuss it during the class.